So we can take this representation of water and we can simplify it. So basically what we're showing here is we're showing oxygen with its 6 valence electrons and hydrogen with its valence electrons and how we have formed this covalent shell. And we're just representing the valence electrons here. But one of the things that we will notice is that because oxygen has a higher affinity for electrons than does hydrogen, sometimes one of these hydrogens can pop off and wander off somewhere, leaving its electron behind. So what that leaves us with over here is what we call a hydroxide ion. It is called a hydroxide ion because it has a hydrogen and an oxygen, plus it has this hydrogen's electron, so it's negative. So this is now hydroxide ion, and this thing that popped off is hydrogen ion because it's now missing an electron. And if you remember that hydrogen is basically a proton that is orbited by one electron, if you lose your electron, then you're a proton. So hydrogen ion is synonymous with proton because typically what you have here is just going to be a lone proton. Now, when we get into our discussion of what is an acid and what is a base, an acid is anything that puts hydrogen ion into solution. So we call these hydrogen donors or proton donors. A base is anything that will take hydrogen ion out of solution. So as much as we have water can spontaneously dissociate like this, we also would have hydroxide ion and hydrogen ion getting back together to form water. In fact, if you look in plain, pure water, you will see that this happens spontaneously. We will have the spontaneous dissociation of water into hydroxide ion and hydrogen ion. But at the same rate that water dissociates into hydroxide ion and hydrogen ion and hydroxide ion will get back together to form water. So we have this reaction that is running in both directions simultaneously at equilibrium. So that means that for every water molecule that dissociates, somewhere else, a hydroxide and hydrogen ion are getting back together to form water. And if we look in pure water, let's say we had 1 liter of pure water, and we looked at how much hydrogen we had, we would find that we have 10 to the negative 7 mole, which is a very small concentration. We would have 10 to the negative 7 mole of hydrogen ion. By the same token, we would also have 10 to the negative 7 mole of hydroxide ion. And this 10 to the negative 7 is going to be how we define our pH scale. And this scale, you've probably seen it before, ranging from 0 to 14, that tells us the concentration of hydrogen ion in solution, and therefore we call it the power of hydrogen, or the pH scale. Now when we look at the pH scale, we will see that 7 is neutral. And 7 corresponds to 10 to the negative 7 mole of hydrogen ion per liter of water. And so what we end up with is, if we have something that puts more hydrogen ion into solution, then we increase the concentration. So the pH of 6 would correspond to 10 to the negative 6 mole. 5 would correspond to 10 to the negative 5. So as you see, we are increasing the concentration of hydrogen ion in 4, 3, 2, 1, and 0. By the time you get to 0, you'd get to 1 mole. So that's quite a bit of hydrogen ion. Now, if we decrease the concentration of hydrogen ion, then we would get to 10 to the negative 8 mole. So basically, this goes all the way out to 14. What we have is a logarithmic scale that we have turned from negative to positive and simplified this whole thing just by having a scale where 7 is neutral that ranges from 0 to 14. Now, actually, in reality, you can actually go outside the scale. You can have values even less than 0 and greater than 14, technically. But typically, in most situations, we rarely see a pH outside of the scale. If the only thing that you remember about the pH scale, and you don't remember anything about the derivation, the important thing that you remember about the pH scale is that 7 is neutral. So this is what pure water should be. 0 is very, very acidic. Anything less than 7 is acidic. Anything greater than 7 is basic, or what we call alkaline. And so 14 would be very, very alkaline. And anything on either end of the scale is going to be quite reactive. So very strong acids and very strong bases tend to react with things, and they're quite caustic. And so on the very alkaline end of the scale, we find things like drain cleaners. And on the very acidic end of the scale, we find things like cement cleaners. And we'll talk a little bit more about some of the properties of acids and bases a little bit later on, and we'll show it in the lab. But it's important to remember one other feature about this scale. Because it is logarithmic, that means that with any change that we have, so from 6 to 7, we have a 10-fold increase in the number of hydrogen ion. So that as we go towards 0, for each number on the scale, we have a 10-fold increase. So if we go back to our molar concentrations, 10 to the negative 7 is neutral. So if we had 10 to the negative 6, which is slightly acidic, that's going to be a 10-fold concentration in hydrogen ion more than we have at neutral. 10 to the negative 5 is going to be a 10-fold concentration more than 10 to the 6. So in other words, for each number on the pH scale, we're having, when we go towards 0, a 10-fold increase. So 6 has 10 times more hydrogen ion than 7. 5 has 100 times more hydrogen ion than 7. 4 has 1,000 times more hydrogen ion concentration than 7, 10 times more than 5, and 100 times more than 6, and so forth. So that basically, if we go in the left direction towards 0, we're getting more acidic, and we're getting a 10-fold increase in hydrogen ion with each step we take. Now, as we go to the alkaline end of 14, we're taking a 10-fold decrease in the amount of hydrogen ion. So if we get out here, 10 to the negative 8, basically we're becoming slightly basic, and we keep decreasing the concentration of hydrogen ion out to 10 to the negative 14, which is an extremely infinitesimally small amount. But to simplify all of this, once again, we can take 7 as neutral, 0 is extremely acidic, and 14 is extremely basic. And now that we have defined exactly what an acid and a base is, an acid, once again, is a hydrogen donor or gives up hydrogen ions in solution, and a base is something that accepts hydrogen. So one of our most common bases would be hydroxide ion. So we could say that water is acting both as an acid and a base simultaneously, because not only does it give up hydrogen, but for every hydrogen ion that is put into solution by the dissociation of a water molecule, elsewhere in that same solution we'll have a hydroxide ion and a hydrogen ion spontaneously getting back together to reform a water molecule. So while we have the basic component of water here and the acidic component of water here, they're always exactly balanced, and this is why we consider it neutral. Now, if we look at other acids and bases, we will see that they change the pH because they will add to the hydrogen ion concentration if they're an acid. So let's look at a very strong acid. Let's look at hydrochloric acid. Hydrochloric acid basically is hydrogen and chlorine. And if you put this in water, it will dissociate into chloride ion and hydrogen ion. And this will dissociate completely. So all the hydrochloric acid molecules that you put in water will dissociate, so you have nothing left but hydrogen ion floating around in water and chloride ion floating around in water. So the fact that this dissociates completely makes it a strong acid. And this, if you have a high concentration of hydrochloric acid, is quite caustic. It's what is used as muriatic acid to clean concrete. Now, let's look at a very strong base. A strong base also completely dissociates in water. And let's look at sodium hydroxide. So again, we have sodium and we have hydroxide. And when you put this in water, they will dissociate into sodium ion and hydroxide ion. And hydroxide ion will immediately start picking up any hydrogen ion that is in solution. So it will decrease the concentration of the hydroxide or hydrogen ion, because hydrogen ion will immediately form water with any hydroxide ion that's put into solution by the sodium hydroxide. And this too wants to react with stuff, is very caustic, and it's the kind of base that we find in things like liquid Drano and drain cleaner. So as you can see, both of these compounds, both the hydrochloric acid and the sodium hydroxide, are very caustic. Now let's look what happens if you react the two together. So if you take hydrochloric acid and mix it with sodium hydroxide, and if you were to do this in the lab, you would have to be extremely careful because you would get an extremely vigorous reaction, and one that could pretty much explode in your face if you're not careful. But since we're not doing this in the lab, I'll just simply write it out on the board. Fortunately, we don't have to worry about having a mess. So if we mix hydrochloric acid with sodium hydroxide, we would find, sort of running out of board space here, that these things would dissociate completely. So we would have a complete dissociation of hydrogen ion, chloride ion, sodium ion, and hydroxide ion. So these things would now be floating around in water, but not for long. Because if you look carefully, you will probably see that we have a great possibility for an exchange reaction. And so we would take the hydrogen and the hydroxide, and guess what? Let me just draw an arrow around this way. They would recombine to form water. So we would have water forming from the hydrogen ion and the hydroxide ion, and of course we would have our salt, sodium chloride, which in solution would actually still be dissolved sodium ion and chloride ion. But if you were to evaporate the water off, you would be left with salt crystals. So that when we react a strong acid and a strong base, we would get water and salt.